Hi there everybody, it's Mr. Pope from Wilmington Grammar School for Boys, and today I'm going to be looking, this is the third session, calculus. Let me just check. Yep, it is. And I want to be looking at some more advanced differentiation techniques, mainly for one variable calculus. So, okay, how do we differentiate things? How do we take ordinary derivatives and more complex functions? Well, at the moment, I've only taught you the power rule for polynomials, okay? And that is, if I have a polynomial, k times x to the power n, that if I want to differentiate that with respect to x, then I bring the n forward as a factor, so that's n times k, and then I lower the power by 1, so n becomes n minus 1. Yeah, that's pretty straightforward. Now, and I've also shown you from first principles what that means. So if I want to find the derivative of a function f of x, i.e. differentiate a function of f of x, then that is the limit as h tends to 0 of the function when you evaluate it at some increment x plus h away from x, or just h away from x, subtract f of x all over h. And the reason for that is because when we're differentiating, we're finding the gradient of a function. So if here's my function, if I take this value to be my x, and it outputs a y value, say f of x, where this is the graph y equals f of x, and I move forward some amount h, so this point here is x plus h, and that point here corresponds to a y value of f of x plus h, then the gradient between these 2 points best approximates the gradient of the curve, the tangent at that point, if this distance h tends to 0, i.e. make it as small as possible, infinitesimally small. And really, if you're okay with these concepts, then you're ready to move forward. If not, go back to the previous video, try some things out, get your head around it. I personally suggest a couple of other YouTube videos. I think 3 Blue, 1 Brown Essence of Calculus course is amazing. I think the graphics are a lot more detailed on here. I think the only thing that my videos can possibly offer over that is maybe some specific examples and slightly more tailored approach to maybe the British school curriculum. But otherwise, I think the 3 Blue, 1 Brown videos are absolutely amazing, and there's no way I could hope to do animations as good as that. So, okay, now you're thinking, okay, so I know what a derivative is. I know it's finding the gradient of a function when I differentiate with respect to x. You can use derivatives to solve optimization problems. And also, you know how to differentiate polynomials, but you're probably thinking, okay, but then what about trigonometric functions like sine of x? What about cosine of x? What about tan of x? What about the exponential function that you've shown me before? What about the logarithmic function that you've shown me before? And so on, and so on, and so on. Right, so what I'm going to do is I'm going to give you a table of these derivatives you need to memorize, and then I'm going to show you where they come from and how they came to be. So here is my table of derivatives you're going to need to memorize. So if this is my f of x, then this will be my f dash of x. So what do they each differentiate to? Well, sine of x, curiously enough, differentiates to cosine of x. And cosine of x differentiates to minus sine of x. And we'll get into it a little bit later, but sine x and cosine x, they differentiate in like a chain. So if we start with sine x, which I'll call s, that will differentiate to cosine of x, and cosine of x will differentiate to minus sine of x. Minus sine will differentiate to minus cosine, and then minus cosine will differentiate to sine. And by the way, this works for differentiation, And if you reverse the process, i.e. go backwards around the circle, then indeed you've got something useful for integration as well. You don't have to memorize it that way, but I feel it's somewhat helpful. Tan of x is an interesting one because that actually differentiates to 1 over cosine squared of x, or as we'll see later in the trig chapters, secant squared of x or sec squared x. E to the x, well, by definition, we'll be looking at later, especially in the next calculus episode when we'll be looking at Taylor series and Maclaurin series, other series expansions as well at later date, like the Laurent series. E to the x just differentiates to itself. Okay, and if you think back to a previous video I made, I said the e to the x function is very special, i.e. the y value is also the value of the tangent, the gradient of the tangent at that point, and it's also the value of the area under the graph from negative infinity up to that point. So this shouldn't be as a surprise. The y value, f of x, should be the same as the tangent f dash of x, and that's mainly by construction. I mean, I'll be looking at that in more detail in another video, but I think I've constructed it to be that way in previous ones. Now, with ln of x, or natural log of x, this differentiates to 1 over x. Now that's particularly interesting, and we'll be covering that shortly. Okay. Right, so to differentiate these things, we're going to have to define a few things, and it's going to have to take a little bit of a step back. So let's start with sine of x becoming cosine of x, and in a way, by tackling this problem, I'm actually going to deal with sine of x, cosine x, and tan of x. And I'll talk about what I mean by that. So first of all, we're going to start at the beginning, and that is, if I want to differentiate sine of x with respect to x, then I need to find the limit as h tends to 0 of sine of x plus h minus sine of x all over h. Okay, now all I'm doing is I'm mimicking by first principles how to differentiate, and my f of x function is my sine of x, so x plus h is going to be put into my sine function like so. Okay, that's all I'm doing. So really we need to evaluate this, and on the surface of it there's not a lot we can do here unless we actually know, well, what happens when we do sine of x plus h. Okay, and we're going to have to take a step back a little bit here, and there's various ways we can do this, but what I'm going to do is I'm going to ask you to consider, actually let's do this up here, so let's consider the following construction. Okay, now you're going to have to put your imagination caps on here. I've got a flat piece of ground like so, and I've got a wedge, a triangle like so, where that's a 90-degree angle, and this angle we'll call x. Okay, and for the record, the hypotenuse is also 1. Okay, next up I'm going to stack another wedge on it, so its point is like this, and this is also going to be a 90-degree triangle like so, where this hypotenuse is also equal to 1, but now this angle here is h. Okay, and now what I want you to consider is this new triangle, which if I drop a vertical from the highest point of the wedge like so, so this is 90 degrees, then I've got a triangle here like that, and then clearly the total angle in this bottom left hand corner is going to be x plus h, because I'm just adding the angle x and adding the angle h together. And therefore, if I wanted to find out what sine of x plus h was, that would be the opposite, which is the total height, divided by the hypotenuse, which we've defined to be 1. So in other words, sine of x plus h is just the height of this triangle. Okay, so that's something we can work towards. How about we define a few other bits? For example, if I look at the bottom triangle, which has an angle of x, then this length here is the adjacent, and the hypotenuse is 1. So I can tell straight away that cosine of x is that adjacent over its hypotenuse, which is 1. So clearly the length of the blue segment here is cosine of x. By similar argument, this is the opposite. So opposite over 1, which is just the opposite, is sine of x. So this height here is sine of x. By similar reasoning, the distance from here along to here, the base of the triangle up above there, is just the adjacent over hypotenuse of 1 of cosine of h. So this is cosine of h. And you can probably tell that the height of this triangle here is going to be sine of h. Now this becomes a lot easier to deal with when we've defined both of the triangles to have an hypotenuse of 1. And that's the whole point of doing it. So this length here is cosine of h. Okay, now essentially what I'm going to be doing is I'm going to be breaking this up into 2 bits. I'm going to be drawing a parallel line with the ground here, so this is 90 degrees, dropping a vertical down here like so. And now it's pretty obvious that all I have to do is add this orange height that's highlighted with this green height, and now that will just be the height of the thing. So let's have a think. Well, let's see if there's any other angles that are the same. So, are there? Well, I know this looks a bit crazy, but if I draw with a purple line, dush, 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 we've got alternate angles going on here. So that means this angle here is also x, which means this angle is 90 minus x, and if 90 degrees is there, then this angle is x. Okay? And now if we consider this top triangle here, I want the adjacent, I've got an angle and I've got the hypotenuse. So adjacent hypotenuse means that cosine of x equals the adjacent, which is the orange bit, over the hypotenuse, which is sine of h. So immediately, if I multiply by sine h both sides, then sine h times cos x is just that orange height bit. Okay, so immediately I know that sine h times by cos x is one part of the puzzle, so I can copy that down and put it here. And then I'm going to have to add the green height. Now I'm hoping you can see that the green height, if I move it horizontally to the right, or if I just draw it, it's the same as this height over here. Now we're going to play a little trick, because I know that this angle is the same as this one. So by similar triangles, the triangle that has an angle of x, and this is cosine x, this is sine of x, and this is 1, must be similar to then if I drew the smaller triangle, such that hypotenuse now is cosine of h. The height, I don't know what it is, but the angle is still x. So we have to think to ourselves, what do I have to multiply 1 by to make it cosine h? Well, I multiply by cosine h. So then I have to multiply sine x by cosine h to get the new scaled down height here. So in actual fact, this height here is sine x times by cosine h. And now I've got an expression for the height. So the final result is sine of x plus h is sine h cos x plus sine x cos h. I could have written that in another order, but essentially that's what it is. So now I'm free to evaluate this. So this is going to be the limit as h tends to 0 of, and what was it again? It was sine of h times by cosine of x plus sine of x times by cosine of h minus the sine of x, and this was all divided by h. Okay. Right. Now, what I'm going to do is I realise that there's some cosine x terms and there's some sine x terms here, so I'm going to collect them. Okay, so this is still the limit as h tends to 0 of 1 over h times by the cosine x terms are cosine x times by sine of h, and then plus the sine x terms, lots of, there's a cosine h there and there's a minus 1 there, so this is cosine h minus 1. And if I redistribute the 1 over h into this, then the 1 over h goes into here and the 1 over h goes into here. And now we're ready to roll. Okay, so now what have we got? We can redistribute the limit in there. Now because x doesn't depend on h, this means I've got cosine x lots of the limit as h tends to 0 of sine of h over h. So that's something we need to evaluate. Plus, and since the sine x here doesn't depend on h, we can take that out as a factor. So this will be sine x times by the limit as h tends to 0 of cosine of h minus 1 over h. Okay, now we're going to have to evaluate both of these limits when h tends to 0. And one of them is easy, one of them is a little bit tricky, but they're both doable. So the first one I'm going to start with is this sine of h over h1. Now that's the trickier one, and you're going to have to bear with me a second, because I'm going to ask you to consider the following shape. If I have a circle centered at the origin, that's a circle, and it's got a radius of 1. Okay, if I draw a line from here to there to form a triangle. Now I always get this part of the proof a little bit mixed up, so I'm probably going to include multiple things than I'm supposed to. But let's suppose that this angle here is h measured in radians. Then if I drop a vertical line down like so, so this is 90 degrees, then as I said before, the cosine, i.e. the width of this thing, is the width of this is cosine h, because cosine of h is the adjacent over the hypotenuse, and if the hypotenuse 1, then it's just that width. And then similarly, this height here must be sine of h. Okay, now there's a couple of shapes I want you to consider. First of all, if we consider this triangle, this green triangle here, okay, what is the area of that triangle? Well, the area of that triangle is a half of base times height. So it's cosine of h times by sine of h, and this is all over 2. Okay, and I'm going to shade that green to remind ourselves that was the green triangle. Okay, next up, what is a next larger shape we can consider? Well, if I consider this shape, that orange triangle, do you agree that it's larger than the green triangle? And what would that triangle's area be? It would be half of base. So this is going to be smaller than half the base. Well, the base is 1 because it's a radius of 1. times by the height, which is still sine h, and then that's over 2. So this is just going to be sine of h over 2. And I'll shade this orange to remind ourselves it was the orange shape. Next up, what's the next largest shape we can think of? Well, if I shade the sector, i.e. that portion of the circle, do you agree that that's larger than the orange triangle? And we now know, since doing our radians work, what the area of this sector will be. It's just half of r squared times by the angle. So this is smaller than half of 1 squared times by angle, so it's h over 2. Okay. Now this is fairly straightforward. I'll shade this red to remind ourselves it was the big sector. So round bit there. So that's the roundy bit. This, I'll probably use a smaller thing. It's just to indicate it was the triangle. Okay. Right. Now let's do some algebra with this. For a start, we can multiply all of them by 2. So if I do that, there's no longer any fractions, like so. And then since h is a positive constant, I can divide everything by h and it should be okay. So if I divide by h, this becomes over h, this becomes over h, and h over h becomes a 1. Okay. I think maybe I need to back it up. I think I've missed out one shape. Let's back it up. Over 2, over 2, over 2. Right, okay. There's one more shape I think I needed to include. And that was, I always get this wrong, is if I was to extend this line like so, such that if I drew a perpendicular line to the x-axis, it creates a right-angled triangle like so. And now I've got the largest shape of all, which is this right-angled triangle here. Then that is clearly the largest areaed shape. So it's got a base of 1, but what's the height? Well, it's clearly a similar triangle to the original one. So if the original one, if you remember, was sine of h and cosine of h, and it had a hypotenuse of 1, I want that to be similar to the larger triangle with base of 1. And now what would the height be? Well, what do I have to do to go from cosine of h to 1? I have to divide by cosine of h. So this new hypotenuse is sine of h divided by cosine of h. So now the largest triangle is just going to be base, which is 1, times by sine h over cosine h, half of that. So this is clearly going to be smaller. So this is the biggest one, so this is going to be sine of h over 2 lots of cosine h. And that corresponded to the largest triangle outside of the circle. Like so. Okay, now we're ready to roll. So, the first thing we're going to do, again, same deal. We're going to multiply by 2, so these all disappear. Actually, I don't think I need the last one anymore. I knew we needed to compare 3. So I'll take these shapes. Now what do? Well, we're going to divide by sine h on both sides. So this becomes 1 is less than h over sine of h, and this is less than 1 over cosine of h. Now, if we reciprocate everything, then the inequalities flip, right? The reason for that is if I've got a half is less than 3, if I reciprocate both sides, then 2 isn't less than a third anymore. So we need to rectify that. I can divide by sine h because sine h is going to be a positive height, so that's not going to flip the inequality. and even if it does, it's not going to change my point, as you'll see in a second. So if I flip everything, 1 over 1 is still 1. That's greater than sine of h over h, and this is greater than cosine of h. And now, if I let h tend to 0, which is what I was wanting over here, then cosine of 0 is just 1. So now I'm essentially saying that sine of h over h is squashed between being lower than 1 but greater than 1. And technically you could argue that when h tends to 0 that all these things kind of are less than equal to each other. Worst case. So what this is the idea of something called a squeeze theorem, because I'm manipulating in such a way that I'm squeezing this value to be between two values which happen to be the same. How can a number be less than or equal to 1 or greater than or equal to 1? It must mean that sine h over h is 1. So this whole thing over here will just simplify down to 1. So far we've got cosine x times 1, which is just cosine x. And now I'll box this off. So this was the squeeze theorem, quite important. Actually, no, that wasn't part of it. It's very important, squeeze theorem. And the next part is we're going to have to consider cosine h minus 1 all over cosine h. And the way we're going to do that is we're going to multiply by cosine of h plus 1. And you're going to be thinking, okay, why are they doing this? So cosine of h minus 1 over h, and I'm going to multiply by cosine of h plus 1 over cosine of h plus 1. And by the way, a fraction with the same numerator as denominator is just 1. So multiplying by 1 shouldn't change the result of this. Now, I've got a difference of squares on the top, so I'm going to have cosine squared of h minus 1 on the top. And on the bottom, I'll have h multiplied by cosine h plus 1. Okay, right. So how does that help at all? Well, if I look back at this triangle over here and remember, well, just in general, that if I've got a right angled triangle where this angle is h and this is 1, and this is sine of h and this is cosine of h, then clearly cosine squared h plus sine squared h equals to 1 by Pythagoras. So if I subtract 1 from both sides to get cosine squared of h minus 1, and I subtract sine squared from both sides, this becomes minus sine squared h. So in actual fact, I can replace this cos squared h minus 1 with just negative sine squared h. So that's exactly what I'm going to do. So this thing actually becomes negative sine squared h over h times by cosine h plus 1. Now I can't go substituting h equals 0 in just yet, because I've got an h on the bottom, so that would be a 0, and I've got sine squared of h on the top, that's going to be a 0 as well. But the trick to this is we're going to take a factor of minus sine out of the top. So do you agree that sine of h over h multiplied by minus sine of h over cosine of h plus 1 is the same as the result before? Look, if I do sine times minus sine, that will give the minus sine squared, and h times the bottom, that will give the bottom as well. So this is consistent. Now, I've already proven by the squeeze theorem that sine h over h is just 1, so that's fine. Now if we look at the right hand side, when I substitute in 0, this works out nicely, because on the top I've got minus sine of 0, which is minus 0, which is 0, over cosine of 0, which is 1, plus 1 is 2. And now minus 0 over 2 is a nice easy thing to deal with, it's just 0. So the result is going to be 1 times 0, which is just 0. So this term, unfortunately, the limit as that just becomes 0. So I've got 0 times sine x, which disappears. And thus, I have proven that the derivative with respect to x of sine x is actually cosine x. Now, I could spend another 20 minutes or so going through how you do it with cosine and tan of x, and I'm more than happy to do that, except this video would probably take another 40 minutes or so because I've gone quite slowly. But I'll break it down to you with spoilers. What I would do is I would start with from first principles of what sine and cosine of x is. I would probably have to deal with what cosine or tan of x plus h is. To consider that, I would draw a similar diagram, which, to be fair, when you're more familiar with trigonometry, you'll be able to spit out these results as and when fairly quickly. But if you don't know, then I would draw a similar diagram and think about what tan of x plus h or cosine of x plus h means. I would then evaluate the limits, and if there was any problems, i.e. any limits when I was doing a 0 divided by 0, I would probably do a similar technique of, basically checking, can I split this limit up into something where it's not a 0 over 0, and does it make sense? Essentially, when you're trying to resolve a limit and you've got a 0 over 0 case, which is called indeterminate, right? Whenever you're dealing with a limit of something, and this is a fraction, let's say g of x over f of x, for example, and this turns out to be 0 over 0, this is indeterminate. I can't spell. Indeterminate. This is indeterminate. You cannot determine what this thing is. So there's various tricks to deal with this. As I've shown before, you can kind of do this kind of rationalizing denominator trick, you can split the limit up. Later on in the calculus course, we'll be looking at L'Hopital's rule, which, to be fair, sorts out 99.9% recurring of all things when they're in determinate form. But essentially that's what you need to do. I suggest, if you want to check to see if you've really got this, can you follow a same logical argument of showing that cosine x differentiates to minus sine x and tan of x differentiates to 1 over cosine squared x. And by the way, if you don't want to go through this rigmarole every single time, I suggest you just memorize this. It's really useful. Moving forward, it's expected of A-level students to just have this memorized. Okay, it saves a lot of time. All I'm doing is just showing the proof of where it comes from, just so that you know, and you can say, oh yeah, I saw the proof of it once, I know it's a thing, but whatever. Okay, now, E of x. Now, this is a little bit more difficult. When I say difficult, there's just more steps involved. If I wanted to differentiate e to the x, that is by construction just e to the x. Okay, to prove this, by construction, we said that y equals e to the x. If this is x and this is the exponential function, then it has an output of e to the x, and we defined it such that the gradient of the tangent at that point m is also e to the x, and the area under this curve up to that point from negative infinity up to that is also having an area of e to the x as well. It's everywhere. But let's suppose that we didn't know that and we want to define this. So we've got e to the x. To differentiate that from first principles, then we want the limit as h tends to 0 of e to the x plus h, because that's what f of x plus h is, minus e to the x, and this is all over h. Okay, same deal. E to the x plus h is the same as e to the x times by e to the h, because that's how indices work. And this is minus e to the x, and this is all over h. And this is the limit. as h tends to 0. Okay, the top, the numerator, has a common factor of e to the x. So if we take that out, this is e to the x lots of e to the h minus 1 over h. And this is the limit as h tends to 0. Okay, now because x doesn't actually depend on h, we can take that out as a constant. So e to the x times by the limit as h tends to 0 of e to the h minus 1 all over h. And bearing in mind that this is all equal to what happens when we differentiate e to the x. Okay, now there's another little clever technique we're going to pull here. On the left hand side we've got f dashed of x, where f of x equals e to the x. And on the right hand side we've got e to the x. And now let me write it another way. Let's suppose I've got the limit as h tends to 0 of, now e to the h is e to the h plus 0, and 1 is the same as e to the 0, and this is all over h. And if you think about this really carefully, this is essentially the same as the derivative of f, but evaluated when x is 0. So what we've actually got is e to the x times by f dashed of 0 equals f dashed of x. Now, there's various ways of also proving that e to the x differentiates to itself, but I think this is probably one of the more compelling arguments. The reason I say that is because, well, what does this become when x equals 0? Well, on the left hand side we've got f dashed of x is 0. On the right hand side we've got e to the 0, and we've also got f dashed of already 0. Well, we're just showing that 1 equals to 1 at this case, so it's fairly consistent. Now there's lots of other arguments to be had, and this will be made more clear when we look at the Taylor series and Maclaurin series of e to the x. But what we've got really is that e to the x has to differentiate to itself. Okay, look how consistent that would be, because what we're saying is f dashed of x would be e to the x, because we're assuming it differentiates to itself. That will equal e to the x times by, and now we're saying differentiate e to the x, which is itself e to the x, and then sub in 0, and e to the 0 is 1. So this is logically consistent. This statement says that the solution is e to the x is its own derivative, because when x tends to 0, yeah, you've got stuff going on that just makes more sense. Now, to prove that the natural log differentiates to 1 over x, we've got to look at the exponential in a slightly different way. Now, there's various ways of doing this. Indeed, we need to look at the Taylor series, which we'll do later. But another way of writing e to the x is that it's the limit as, I don't know, let n tend to infinity of 1 plus x over n to the power n. And this is to do with infinitely compounding interest. You'll actually see this. Well, I tell you what. Let's just do the Taylor series so you can see where it comes from. Okay, so let's suppose I wanted to expand 1 plus x over n to the power n. Okay, Now, the binomial expansion of this, well, let's just deal with it. Let's just think about what the binomial expansion would be. Let's say I've got 1 plus x to the power of n. And let's just deal with a couple of terms. Let's say I'm dealing with n is 1, then n is 2, then n is 3, then n is 4, and so on and so on. When n is 1, I'm just going to have 1 plus x. When n is 2, I'm going to have 1 plus 2x plus an x squared. When n is 3, I'm going to have 1 plus 3x plus 3x squared plus x cubed. When n is 4, I'm going to have 1 plus 4x plus 6x squared plus, 4x cubed plus x to the 4. And so on and so on and so on. Now, as you can probably see, there's a pattern going on. We're always going to start with 1. Now the next term, it might not be so obvious, but this is just going to be n times by x. And then the next term, if it exists, well, check for yourself, but this is going to be n times by n minus 1 over 2 factorial, and then times by x squared. Let's think about that. When n was 3, I'd have 3 times 3 minus 1, which is 2, all over 2 factorial, which is 2 times 1. Those 2's cancel, so I'm left with 3. Oh look, that's going to work. When n was 4, well, I'm going to have 4 times by 4 minus 1, which is 3, over 2 factorial again. 2 factorial is 2, so that 2 and the 4 can cancel. 2 times the 3 is the 6, that will work. And you can try this yourself with other ones. And the reason why this works is because there's combinatorics, there's counting methods going on at here. Long story short, the next term will be n times n minus 1 times n minus 2 all over 3 factorial. And if you think about it, n times n minus 1 over 2 factorial is the same as n factorial over n minus 2 factorial times by 2 factorial. And as I've said in a previous video, this is n choose 2. And if you think about it, n is the same as n choose 1, and 1 is the same as n choose nothing. So really what I'm saying here is when you've got this, it actually becomes n choose 0 plus n choose 1 of x plus n choose 2 of x squared plus n choose 3 of x cubed plus, and you can just keep going for as long as you like. Now, if I look at what I'm claiming it to be with the exponential function, let n tend to infinity, right? Then what do I have? Well, what did I say? I said the limit as n tends to infinity, that is a terrible infinity, of 1 plus x over n to the power n. So the first term is going to be 1 plus this, whoops daisy, n choose 1, which is n, times by this term, which is x over n. So the n's cancel, so we're left with 1 plus x, plus next term, n choose 2, which is n times by n minus 1 over 2 factorial, times by x over n all squared. Now let's deal with that. I'm going to have an n times n, which is n squared, times by the x squared over 2 factorial n squared. And then I'll have n times minus 1, which is minus n, times by the x squared over 2 factorial times n squared. If I tidy this up, the n squareds cancel here and here. The n will cancel that n squared somewhat, and we've got the next term. Now, the next term, I'll do it, is n times n minus 1 times n minus 2 all over 3 factorial, which is 6, times by x over n all cubed. This thing here is going to expand to n cubed minus 3n squared plus 2n. So the first term with the n cubed is going to be plus n cubed x cubed over 6n cubed. The next term is going to be minus 3n squared x cubed over 6n cubed. And the final term is going to be plus 2n x cubed over 6n cubed. And if we tidy this up, the n cubes are going to cancel here and here. The n squared is going to cancel with that. The n is going to cancel. That's going to be an n squared on the bottom. Okay. Right. Now, here's the great thing. Because n is tending to infinity, all these fractions with n on the bottom are going to tend to 0. Because if I divide by a number that's tending to infinity, it's going to disappear and tend to 0. So really what we're left is this sequence, this limit as n tends to infinity of 1 plus x over n to the n, this is going to tend to be 1 plus x squared over 2 plus x cubed over, well that's 2 factorial, 6 is just 3 factorial, let's not mess around, and so on and so on. And you can probably see the next term will be x to the 4 over 4 factorial, and so on and so on and so on. You can do this as much as you want. Essentially, it's the same as the sum from r going from 0 up into infinity of x to the r over r factorial, if you want to put it in a condensed pocket like that. Okay, so how do I know that this, well, okay, if this does truly equal to e to the x, then if I differentiate this, it should be the same thing. So if I differentiate the left-hand side, then I have the derivative with respect to x of the limit as n tends to infinity of 1 plus x over n to the n. And on the right-hand side, what happens? Well, 1 disappears to 0, x disappears to 1, x squared over 2 factorial becomes 2x over 2 factorial, and the 2 and the 2 factorial cancel. The x cubed, well, that becomes 3x squared, and this is still over 3 factorial, but 3 factorial is 3 times 2 times 1, so the 3 and the 3 factorial, that becomes a 2 factorial, and then so on and so on. Look what happens. This becomes 1 plus x squared over 2 factorial. What happens? The process of differentiation means that each term shuffles down 1. And because I've got an infinite amount of terms, it means I've got an infinite amount of places to shuffle down. I'm never going to run out of terms to shuffle down for. So actually, yeah, this limit is e to the x. So in a way, I've kind of derived the Taylor series for e to the x by looking at it hopefully intuitively. Yeah, from a binomial expansion point of view and telling you it's a limit. Now the reason I had to tell you all this stuff is because now I've actually got to, well, let's move some stuff around. Let's move this, because now I've got to differentiate what I promised I would, and that is to differentiate the natural log of x, which hopefully should be a quick enough job now. So this was all consider. And this was all part of the thing. And now we're going to consider, so to differentiate the natural logarithm of x. Well, this is going to be the limit as h tends to 0 of ln of x plus h minus the natural ln of x, and this is all over h. Okay, we can now use our logarithm rules. So this becomes the limit as h tends to 0 of the natural log minus another natural log, just means this can be a combined log of x plus h over x. And this is all over h. And now, what have we got? Well, the fraction inside the ln, we can simplify that down as ln of 1 plus h over x. And this is all over h, so this is actually to the power of 1 over h. And this is the limit as h tends to 0. Okay, now this is actually quite interesting because we can actually fiddle this around a little bit. Let's suppose that we're going to introduce a new variable called n, where n is h over x, right? And the reason for that is because, well, no, I don't want that, sorry. Not n, it's 1 over n, isn't it? 1 over n. Okay, let 1 over n equals h over x, because then what will happen is if x was 1, then the middle bit should be 1 plus 1 over h. Okay, and that's fairly easy to sort out. So, what's going to happen here? Well, as h tends to 0, think about it, if h tends to 0, this quantity tends to 0 as well. H over x tends to 0. And the only way that can happen is if n tends to positive infinity. So, if I exchange the limit, so the limit instead of h now becomes n and it goes to infinity, then now, let's think about it. If I make h the subject, this means that h equals x over n. So then that means 1 over h equals n over x. Is that what I wanted to show? Yes. So now I have the limit of 1 plus h over x, which I've defined to be 1 over n, and then it's to the power of 1 over h, which is the same as n over x. Well, if this is n over x is the same as n times by 1 over x. So I can write this to the power n, and then this is all to the power of 1 over x, and then using our log rules of powers, I'm going to take this out to the front over here, like that. And now it's all falling into place. Because now the 1 over x, this constant factor here, doesn't actually depend on n anymore. So what we can do is 1 over x times by the limit of n tending to infinity of the natural log, that should be a ln, not a ln, don't know why I put a ln, natural log of 1 plus 1 over n to the power n. And now, think about it. If the limit as n tends to infinity of ln of 1 plus 1 over n, sorry, not 1, x to, if this is what e to the x is, then if I replace, this isn't the case. If this is the case, if the limit of 1 plus x over n to the n is e to the x, then if I replace x with 1, then the limit as n tends to infinity of 1 plus 1 over n to the power n is just e to the 1. So this whole thing becomes 1 over x times by ln of e. And since log is base e, ln of e is just 1. Because what that's saying is log of base e equals what? Well, e to the power of what is e, that's just 1. So there you have it. The derivative of the natural log of x is just 1 over x. It's a little bit complicated. I hope you follow, but it can just be sought out from just knowing a little bit of binomial expansion, Taylor series, and just approximating limits particularly well. If this doesn't make sense just now, don't worry about it. You can come back to this video at a later date. We are going to be looking at the Taylor series, the Maclaurin series, Laurent series, and binomial expansion at some point. If you're not particularly interested in this stuff, just let it glaze over you. But the point is, as long as you've memorized this blue table here, then that's the key point for this first bit of the video anyway. If you're particularly interested to see where it came from, then I'm hoping I've given a fairly concrete, although there's probably some holes in it thinking about it, but it's pretty solid. I wouldn't say it's super rigorous, but it can be followed and it makes logical sense. Right, now the techniques of differentiation. Okay, now there's a couple. The first one I want to get on board is the chain rule of differentiation. And so I want to get your head around this kind of concept. And that is, if I've got a function, let's say g, and that function depends on another input, let's say f, and let's say that function f depends on x, then the way you need to build this is that if I want to differentiate g as with respect to x, then this is dg by df. So I differentiate g with respect to f, and I multiply by df by dx, like so. And if you want to, and though this isn't technically what's happening, but the analogy is, the df's are like fractions and they cancel, and you're left with dg by dx. The reason why I like this analogy is later on, when we start looking at partial derivatives, this like causality bubble diagram will help with higher derivatives and for partial derivatives where functions depend on multiple inputs. So this is a really key concept. Why does this work? Well, for various reasons. It's like a knock-on effect. It's got a little bit to do with proportionality. We can get a little bit philosophical here. But I'm hoping the main core analogy is that if you look at the derivatives, the ordinary derivatives, and you look at them, well, okay. I mean, what are these things, dg by df? Essentially, they are measurable changes in g and measurable changes in f multiplied by a measurable change in f over that measurable change in x. Now, all these measurable changes, the change in g, the change in f, the change in x, they're all tending to 0, right? But before they tend to 0, they're essentially going to cancel beforehand. Okay, and then you evaluate what's going to happen. Now, an idea of that into play. So, I don't know, let's pick a really easy one. Let's say I've got 3x squared, and this is to the power 3, and I want to differentiate this. So, according to my chain rule, then my g function is I've got something cubed. Well, I've got f cubed, and my f function is 3x squared. Can you spot how I've got f inside g? This is my f function, and my g function is the bit that it's encapsulated in, i.e. the cubed function. Well, this is really easy to evaluate. So the first thing is I do dg by df. Well, if I was to differentiate f with respect to f, then that's the power rule using polynomials. So the 3 comes down, and then the f drops to a power which is squared. And then I need to find df by dx. So 3x squared will differentiate to 6x because the 2 comes down and the 2 drops down to a power of 1. The rule then says that I multiply these two things together. So 3 times 6 is 18. I'll have an x, which is x, and then I'll have f squared. Now I know what f is 3x squared. So this will actually be 18x times by f, which is 3x squared, squared. Now 3 squared is 9. 9 times 18, well 9 9's 81, double that is 162. I've got an x here, and x squared squared is x to the 4, x to the 4 times x is x to the 5. Okay, so I'm saying the result when you differentiate 3x squared cubed will be 162x to the 5. Now, let's expand this bracket and check to see that we're right. So 3x squared to the cubed, well 3 cubed is 3 times 3 times 3, which is 27, and x squared cubed is x to the 6. If I was to differentiate this, the 6 would come down. 6 times 20 is 120, 6 times 7 is 42, 42 plus 120 is 162, and the x to the 6 would drop a power to give x to the 5. And now you're probably thinking, oh man, that was so much quicker, why did we go through this chain rule stuff? Well, for two reasons. One, this chain rule would have worked if I'd have had a triple layer of functions, i.e. functions of functions of functions. The point is you can keep chaining this rule up, and in this case you'd have to have multiplied by dh by dg. The point is you can add as many layers of complexities as you need to break down a problem, so it's quite powerful. The second thing is this works for every function of x. It doesn't necessarily have to be a polynomial. So for example, let's suppose I want to differentiate, let's say sine of x squared. Okay, so what's going on here? Well, we've clearly got sine. Let's say g is sine of f, where the f function is x squared. Can you see how the x squared function of x is sitting inside the sine function? We've got a function of a function. And that's essentially whenever we use the chain rule. So let's bang it out. I've got my function g depends on function f, which depends on x. And if I want to differentiate my original function, I need to do dg by df. And sine of f differentiates to cosine of f. It's one of the things I wanted you to memorize in the table. And x squared differentiates to 2x. Multiply these two things together, and you'll get 2x times by cosine of f. And I know what f is, that's x squared. So what I'm saying is that sine of x squared differentiates to 2x times by cosine of x squared. And this is really nice because when you get good at this stuff, you can rattle these things out really, really quickly. Okay, now, what have we got? The next thing, there's two more rules. And then I'm just going to go through examples, and that will do. So the next rule is the product rule. Okay, let's suppose I've got a function f of x and it's being multiplied by a different function g of x, and I want to differentiate this with respect to x. Then this is going to be f of x times by g dashed of x, i.e. differentiate g but not f and times them together, and then plus f dashed of x times by g of x, i.e. differentiate f of x but not g of x. Okay, now there's various ways of explaining this. One way you could do is you could use the by first principles and deal with it that way. Personally, I don't want to do that. You can do that for yourself if you want to, if you've got a spare half hour to waste. But what I'm going to do is I am going to do it a bit more intuitively. And if you want the diagrams to this and the animations, then I think 3 blue and 1 brown, or 3 brown and 1 blue. No. 3 blue and 1 brown. I think that their YouTube channel does this so well. It's the Essence of Calculus course and it's the product rule. It's amazing. But to paraphrase it, in case you can't find it, is imagine I've got a rectangle where this width, g of x, and this height, f of x. Then if I want to find the rate of change with respect to x of these functions, then imagine a small slither which will say some change g dashed of x, and some small slither f dashed of x over here. And I want to know how the area, because essentially this is an area, changes as you increase by a dx, a small amount. So what's going on here? Well, you're going to introduce a small rectangle like that, a small rectangle like that, and then a small little rectangle down here. Now the idea is as you increase by smaller and smaller amount of x's, the area of this shape is clearly going to be fx times g dashed of x, which is this thing here. And f dashed of x times by g of x is going to be this thing over here. And now you're probably thinking, well, why aren't we including this thing? Because this is essentially g dashed of x times by f dashed of x. And the point is these increments are tending to 0. So we say they're so minuscule, they just don't matter. Okay, and essentially you're going to have to use that argument up here. Where is it? If you was to use by first principles, you'd probably have some multiple h's or h squareds popping out. And I don't want to get into it, to be honest. I've already spent an hour and 6 minutes on this video. I want to just get this out quickly. But the intuition is that if I want to find the change in x of both functions of how that affects the area, then really it's the purple and green rectangle and how they're added onto the shape that's going to make the most difference. Essentially, when these are infinitely tiny, so say I'm dealing with a thin strip like that and a thin strip like that, that's going to constitute some area. But if I have a tiny little square like that, that's going to tend to 0, as the two other things tend to 0. The purple and green rectangles, when the value of x goes to 0, they're essentially like a coat of paint, whereas the bottom right will just contribute nothing to the corner. But yeah, check 3 blue and 1 brown out if you want more intuition on that. Now, we don't write f of x and g of x a lot of the time. For mathematicians, we just use u and v as functions of x. And the reason for that is because I'm going to be using that quite a lot when it comes to integration, especially integration by parts. And to write it out quicker, it just becomes u v dashed plus v u dashed. It's the same thing, u and v are interchangeable. So an example of this is, let's say f of x, I don't know, let's say I've got y, and let's say y is x squared times e to the x, and I want to find dy by dx. Well, here I've got a function, u, being multiplied by another function, ex. So I'll differentiate the u, which is 2x, and then leave the v alone, which is e to the x, plus leave the u alone, which is x squared, times by v differentiated, and e to the x stays the same, so it's just e to the x. And if you want to be fancy, you can take x e to the x out as a thingy bob, as a factor, and this will become x plus 2. As you can see, the x is there and the 2 pops out there. And this is totally fine and acceptable. To be fair, this answer was also fine and acceptable, but if you want to factorize it, that often helps. Okay, what else? The quotient rule. Quotient rule. Okay, now this one is normally given to you in the formula book, and that is, if I want to differentiate a quotient, which is a function u divided by a different function, this one's, you're going to look at it and think, like, what the hell, how did they get to that? So now this is v u dashed minus u v dashed all over v squared. Okay, how did we get to that? Well, all I'm going to do is I'm going to do the product rule, which is d by dx, but this time I'm going to do u times by v to the minus 1. So what's going to happen there? Well, I'm going to get u times by v to the minus 1 and then differentiated. Please notice the difference between the dashed and to the power minus 1 and then plus u dashed times by v to the minus 1, i.e. you've differentiated the u this time and left the v alone. Okay, so now careful, v is a function of x. So if we call this thing g, then essentially what I've got is g is a function of v, which is a function of x. So to differentiate g with respect to x, I need to do dg by dv, and v to the minus 1 differentiates to minus v to the minus 2, if you used to treat v to the minus 1 like a function of x. And then I need to times it by dv dx, which is, of course, v dashed. And now look what happens. This becomes minus u times by v dashed times by v to the minus 2, and then plus u dashed times by v to the minus 1. Okay, so what's going to happen here? If we tidy this up, this is actually going to be minus u times v dashed over v squared plus u dashed over v. And now if I get it over a common denominator and I times by v here and make that a v squared, then you can clearly see this is v u dashed, which is this bit, minus the u v dashed all over v squared. And that's where it came from. Okay. I can go through an example of that, but essentially, if you want to get it right, you plug your u in, you find out what u dashed is, you find out what v is, you find what your v dashed is, and then you just plug it into the formula. So I don't know, I'll do it really quickly. Let's suppose I want to differentiate sine x over x. Then all I'm going to do is I'm going to write my u is sine of x, my u dashed is cosine of x, my v is x, my v dashed is 1. So this is just going to be vu dashed, so vu dashed is x cosine x minus uv dashed, which is just going to be a sine x, and this is all over v squared, which is just x squared. That's it. There's no real trick to this, you just have to work out the individual components and then plug it all together. What else? Well, there's one other trick Edexcel like to do, and essentially, if I've got this only works for ordinary derivatives, okay, and this just means derivatives that only depend on one variable, and you're only ever going to see that at A level, but at university and beyond, you're going to see partial derivatives, i.e., derivatives that depend on multiple variables. Which is why it's called multivariable calculus, because it depends on multiple variables. So if I've got something like dy by dx, that is the same as 1 over dx by dy. And it's a similar argument to treating them like fractions over here, because essentially they're measurable quantities in the limit as that quantity tends to 0, so you can treat them like a fraction, and clearly 1 over a fraction is its reciprocal. And this is going to be quite important. For example, if x equals to sine y, you might be asked to find dy by dx. And if that's the case, you've got x as a function of y, so you might want to find dx by dy first. And since sine y would differentiate to just cosine y with respect to y, then the job becomes, how do I turn cosine y? Well, how do I turn dx dy into dy dx? Well, I just flip both sides. This becomes dy by dx equals to 1 over cosine y. And if you want to make that a function of x, well, you're going to have to use that sine squared of something plus cosine squared of something equals to 1. So, well, cosine theta is just going to be the square root of 1 minus sine squared theta. And you can clearly see this is going to be 1 over the square root of 1 minus x squared, because I know that sine y is x. So sine squared y, taking 1 take away sine squared and then square rooted, it's just going to be cos of y. So dy by dx in this case turns out to be 1 over the square root of 1 minus x squared. And yeah, that's quite a lot of differentiation under your belt. If you want to go over that and check it for yourself, that's absolutely fine. I'm just going to end the video with maybe half hour or so's examples. So if you want to, pause the video and we'll go through it in a second. Okay, the curve C has equation y equals x over 9 plus x squared. Use calculus to find the coordinates of the turning point. Right, a couple of things. dy by dx equals to 0 when we're dealing with turning points, and this is a quotient of functions. So if the top part is x, u dashed is 1, and if v is 9, oh dear, stop it, and v is 9 plus x squared, then differentiate that, just becomes 2x. So dy by dx is going to be vu dashed, which is 9 plus x squared, minus uv dashed, which is 2x squared, and this is going to be all over v squared, which is 9 plus x squared squared. Now, if I want this to equal 0, the trick to this is only the numerator needs to equal to 0. And if you look at this carefully, that's just asking 9 minus x squared equals 0, which means, which means that x squared equals to 9, so x will equal plus or minus 3. Use calculus to find the coordinates of the turning points. Well, that's either going to be x equals 3 or x equals negative 3, but I need the coordinates, so I need the y coordinates as well. And that's easy. I'm just going to substitute the x values in and see what I get. So what happens? If x is positive 3, I've got 3 over 9 plus 3 squared, which is 9. 3 over 18, I believe, is 1/6. And when x is minus 3, then I have minus 3 over 9 plus minus 3 squared, which is positive 9 again. So I believe that's negative 1/6. So my answers are there. And for part II, given that y equals this, find the value of dy dx at the point x equals a half ln 3. Right, this is a chain rule because I've got a function of x inside a larger function of x. So if I let g equal, say, f to the power 3 halves, where f equals 1 plus e to the 2x, well, in actual fact, let's step it back up a bit. Let's say it's e to the d, whoops, it's e to the d, where d is 2x. Then all I have to do is differentiate them with respect to the variables that are inside them and then multiply them together. So f to the 3 halves becomes 3 halves of f to the subtract 1 from the power, that's f to the half. 1 plus e to the d just differentiates to e to the d because 1 disappears to nothing and e to the d stays the same, and 2x differentiates to 2. So when I multiply all these things together, numbers wise, the 2 and the 3 halves cancel to a 3. I've got e to the d, which is e to the 2x, and I've got f to the half, where f is 1 plus e to the d, which is 2x, and this is all to the power half. Okay, so now I've got dy by dx is 3e to the 2x lots of 1 plus e to the 2x to the power half. And I now want to evaluate this derivative at the point, so straight line, that's supposed to be straight, when x equals a half ln 3. Which, by the way, a half ln 3 is the same as ln of root 3, because I can take this half up as a power, and 3 to the half is the square root of 3. But I'm going to leave it there just because I think things are going to cancel. So this is the same as 3e to the 2 times a half is just 1, so this becomes e ln 3, times by 1 plus e to the ln 3 again, to the half. I think things are going to work out nicely, because the e and ln are going to cancel, so it's going to be 3 times 3, which is 9, times by e and ln will cancel, so this becomes 1 plus 3, which is 4, square rooted, and the square root of 4 is 2, 2 times 9, the answer is 18. So that wasn't actually too bad at all. Okay, next part. A curve C has equation y equals 3 sine of 2x plus 4 cosine of 2x, where x is in radians between minus pi and positive pi. The point A, 0, 4, lies on C. Find an equation of the normal to C at A. Okay, pause it. Give yourself a chance to try it if you want. Okay, right. So, concept time. I don't care what the curve is, say it looks like that. If I find dy by dx, then I will find the gradient of the tangent. But I want the normal, which pops out at perpendicular right angles to it. So therefore, if I find the gradient of the curve at that point, all I need to do is find the negative reciprocal, and that will give me the gradient of the normal. So first things first, dy by dx is going to be, now I've got 3 sine of 2x. So that's going to be 3 lots of sine of, let's say, a, where a is 2x. Chain rule again. 3 sine a is going to differentiate to 3 cosine of a, and, oh dear, and 2x is just going to differentiate to 2. Multiply them together. This is going to be 6 lots of cosine a, which is 2x. And the quicker you get with this, the better. And essentially, you can spot that the argument inside is going to come out as a factor. Cosine differentiates to minus sine, so it's going to be minus 8 sine of 2x. Okay, now I know that the point A, x equals 0. So dy by dx evaluated at the point A means I've got 6 lots of cosine 0, which is 6, minus 8 lots of sine 0, which is 0. Now if that gradient is 6, that means the normal must be of the form y equals the negative reciprocal of 6, which is minus 1/6 x plus a constant. And the only thing I know about that normal is it goes through A, which is 0, 4. So when x is 0, y is 4. So when x is 0, I've got 0 plus c, and y is 4. Clearly c is 4. So the equation of that normal is y equals minus 1/6 of x plus 4. And that is the equation of the normal. Nice and tidy. Okay, a couple of things going on here. Again, give yourself some time to do it. Pause the video. Okay, differentiate with respect to x these things. So x squared times e to the 3x plus 2. Right, couple of things going on here. We're going to need the product rule because there's functions of x's being multiplied together, and we're going to need the chain rule for this thing here. So, first of all, for part A, I, we've got u equals x squared, and u dashed is going to be the differentiation of that, which is 2x. Now, v is e to the 3x plus 2, and v dashed, well, the quick way is you take the argument of this and you differentiate it. So 3x plus 2 is going to differentiate to 3, so you bring that out. And then you remember that e to the something, e to the x doesn't change when you differentiate it, so it's just going to be e to the 3x plus 2. And again, with practice, this is going to be quicker and quicker. So that means the answer for I is just going to be v times u dashed, which is 2x times e to the 3x plus 2, plus, and then x squared times that, which is 3x squared times e to the 3x plus 2. And again, they've both got a factor of x times e to the 3x plus 2 outside, so you can say this actually 2 plus 3x bracket times that. Totally acceptable. You don't have to do it like that, it's totally fine. Although finding equations of tangents and normals and finding out with stationary points is a lot easier if you get into this habit, so I suggest you do it. Okay, we've got cosine of 2x cubed over 3x. Right, easy peasy. This is a quotient. We've got a fraction. It's the same deal. I'm going to have u, my top bit, which is cosine of 2x cubed. U dashed, well, I take the argument, which is 2x cubed, and differentiate it and bring it outside. So 2x cubed becomes 6x squared. And then I times it by whatever cosine differentiates 2, and that's minus sine of the argument left alone, which is 2x cubed. So u dashed is going to be 6x squared times by sine of 2x cubed. V is going to be 3x, v dashed is going to be 3, and now I just apply the rules. It's going to be vu dashed, which is 3x times minus 6 squared, so it's going to be minus 18x cubed sine of 2x cubed, and then minus uv dashed. Is that the right around? I always forget. Pretty sure. Where is it? Vu dashed, uv dashed. Yeah. Vu dashed, uv dashed. Where am I? Yeah, no, I was doing the right thing. Vu dashed minus uv dashed. So that's going to be minus 3 cosine of 2x cubed. And this is all going to be over v cubed, which v squared, which is 3x all squared. And you can leave it like that. There's no demand for simplification at this point. I'd probably leave it like that. For part B, given that x is 4 sine of 2y plus 6, find dy by dx in terms of x. Right, okay, so x is a function of y, so don't divide by 4 and then arc sine things, it's just silly. Let's just find dx by dy. So 4 sine of that, well, if I take the argument and differentiate it, that's 2, so I bring 2 outside, so that's 8. Sine differentiates to cos, that becomes cosine, and then this becomes 2y plus 6. If I flip both sides, then dy by dx is going to be 1 over 8 cosine of 2y plus 6. Okay, so actually, not good, because we want it in terms of x. So let's deal with it for a second. If x equals 4 sine of 2y plus 6, then x over 4 equals sine of stuff. I cannot be bothered to keep writing that out. So that means x squared over 16 equals sine squared of stuff. And I know that since sine squared, which I'm going to call s, plus cos squared equals to 1, then cos squared equals 1 minus sine squared, and so cosine equals the square root of 1 minus sine squared. I've got sine squared, so the square root of 1 minus x squared over 16 equals cosine of that 2y plus stuff. And if I get this over a common denominator, that's the square root of 16 minus x squared over 16. So that's cosine. So if I do that, so this is actually going to be 1 over 8 lots of the square root of 16 minus x squared over 16. This is going to be 1 over 8 times by 1 over 16 minus x squared over 16. So I can flip the surd, so this becomes root 16 over root 16 minus x squared. This is times by 1 over 8. Root 16 is 4. The 4 and 8 cancel, so that's a 2. So actually, you don't have to simplify. I'm being silly now. This is actually 1 over 2 times the square root of 16 minus x squared. And that's fine. Totally acceptable. Okay, apologies for the jump cut, but a student spotted a mistake when I calculated the gradient for this question. So if you want to give it a go, pause the video now. So the curve C has equation x equals 2 sine y. Show that point P lies on C. Well, when x equals root 2, does that equal 2 lots of sine of pi over 4? Okay, now in radians, sine of pi over 4 is root 2 over 2. So when I times that by 2, this 2 here, the 2's cancel and I'm left with root 2, so that does equal that. So yes, the point does lie on the plane. Show that dy dx is 1 over root 2 at P. Well, if I take x equals 2 sine of y, both sides, if I differentiate with respect to x, x differentiates to 1, and 2 sine y becomes 2 cosine y, and then differentiate that with respect to x means we're going to have a dy by dx term. So that just means dy by dx is going to equal 1 over 2 times cosine of the y value. So dy dx evaluated at the point of p is going to be 1 over 2 lots of cosine of the y value, and the y value is pi over 4. Cosine of pi over 4 is root 2 over 2, so this is 1 over 2 lots of root 2 over 2. The 2's cancel, I'm left with 1 over root 2. Now here's the mistake I made. Find an equation to the normal. If the gradient is 1 over root 2 of the tangent, then the gradient of the normal is negative root 2. In the previous edit, I just did minus 1 over root 2, and I forgot to reciprocate it, which led to the wrong answer. So my fault. Okay, so if the gradient is minus root 2 for the normal, right, it's perpendicular to the tangent at that point, and I know that x equals root 2 and y equals pi over 4 at the point of p, then y equals negative root 2x plus c, and if I substitute the points in, when y is pi over 4, it's going to be negative root 2 lots of x, which is root 2 plus c. Root 2 times root 2 is just 2, so if I add 2 to both sides, then pi over 4 plus 2 equals to c. So we're actually going to get y equals negative root 2x plus pi over 4 plus 2. And that will be the equation of your normal at the point P. Okay. Next question, if you want to pause the video, we'll go through it in a second. Okay, the point P lies on the curve with equation y equals 4e to the 2x plus 1. The y coordinate of P is 8. Find in terms of ln 2 the x coordinate of P. Okay, so if y is 8, so we'll just plug 8 in there. This is 4e to the 2x plus 1. If I divide by 4, I've got 2 equals e to the 2x plus 1. If I take the natural log of both sides, I've got ln 2 equals ln of e, so that cancels, so I'm left with 2x plus 1. If I minus 1 from both sides, I've got ln 2 minus 1 equals 2x. And if I divide by 2, then I've got a half of ln 2 minus 1 divided by 2, which is a half, and this equals x. Now the answer wanted it in terms of ln 2, so I'm just going to leave it like that. I'm not going to try and do other weird things, but essentially that's the x value. Part B, find the equation of the tangent to the curve at the point P. Okay, same deal, we're going to have to find out what dy by dx is, and this is fairly easy. We take the argument, which is 2x plus 1, we differentiate it, which is 2, we bring it out as a factor, so 2 times 4 is 8, and e differentiates to itself, so this should be e to the same argument, which is 2x plus 1. Now, if I want truly the value at the gradient of the value of p, then I can substitute in x. But look, see, I'm going to be a bit smart about this. X is this thing. Now I could sub x in straight away, but look, all I need to know is what 2x plus 1 is. Well, I know what 2x plus 1 is, that's ln 2. So if I actually substitute it in an earlier stage, then dy by dx at the point P still satisfies 8e to the ln 2. The e and the ln cancel, 8 times 2 is 16. And that saved a lot of faffing around. So because I want the tangent, I just want the gradient is 16. So I'm going to have y equals 16x plus c. Do I know what the y coordinate is? Yes, it's 8. Okay, so if y is 8 equals 16 times this, well, if I times this by 16, that's the same as 8 ln 2 minus 8, and this becomes plus c. If I add 8 to both sides, it becomes 16. If I minus the 8 ln 2, that becomes the c. So actually y equals 16x plus c, which is plus 16 minus 8 ln 2. And that's perfectly acceptable because a and b are just exact constants, and I found the exact constants. That's totally fine. Okay, and that's it. Lot to take on board today, but so important, so useful, and I hope you get your head around it. Toodaloo.